Welcome back to Space-Time Softmax. Today we are exploring the ultimate limit of machines, the Carnot efficiency. In the early 1800s, the world was powered by steam. The goal was simple: turn heat into work as efficiently as possible. A heat engine operates between two temperatures. It takes heat from a hot reservoir, performs work, and must reject some heat to a cooler one. In 1824, a young French engineer named Carnot realized that efficiency isn't about the fuel, it is about the temperature. He proposed an ideal cycle, now called the Carnot cycle. It consists of 4 reversible steps, 2 isothermal and 2 adiabatic. First, the gas expands at a constant high temperature, absorbing heat from the hot reservoir. This is isothermal expansion. Next, the gas is insulated and continues to expand. Its temperature drops without exchanging any heat. This is adiabatic expansion. To complete the cycle, we must compress the gas back to its original state. This requires work. The gas is compressed at a constant low temperature, rejecting heat into the cold sink. Finally, an adiabatic compression brings the gas back to its starting temperature and pressure. The cycle is complete. The area inside this loop represents the net work done by the engine. But how much of the input heat did we actually use? The Carnot efficiency is defined as 1 minus the ratio of the cold temperature to the hot temperature. It is the absolute maximum. Remember, these temperatures must be in Kelvin. This reveals a profound truth about our universe. To reach 100% efficiency, the cold reservoir would have to be at absolute zero Kelvin. But absolute zero is physically unattainable. This means no heat engine can ever be perfectly efficient. Some heat must be wasted. This is a direct consequence of the second law of thermodynamics. Energy tends to spread out, and turning it back into concentrated work has a tax. Real engines are even less efficient. Friction, air resistance, and rapid cycles pull us far below the Carnot limit. To get closer to the limit, we increase the hot temperature. This is why modern turbines use advanced ceramics to survive extreme heat. We can also lower the cold temperature, but we are limited by the environment. Most engines just dump heat into the air or water. From the earliest steam pumps to the jet engines of today, the Carnot limit remains our unbreakable ceiling. It is not just a technical constraint. It is a fundamental rule of reality. We cannot win, and we cannot even break even. Understanding these limits helps us design better tech and grasp the deep structure of our universe. Thanks for watching. Next time we will look at phase changes and why boiling is weirder than you think. Stay curious.